Yeah. So today we will more study the tabular space on two orbifolds. Okay. So we'll cover about half of this today. So first of all, what's the definition of the tabular space of two orbifolds, and then we talk about geometric cutting and pasting of deformation spaces, and the decomposition of two orbifolds into elementary orbifolds, and the tabular space of two orbifolds. So I guess you can do this for just the tabular space of surfaces as well, but from the point of view of hyperbolic geometry, so that's usually called the freecast space instead of tabular space, because tabular is more on the conformal space sort of structure or complex structure. So usually you want called geometric tabular space, freecast space instead. Yeah. Right. So we will just go over some references. So these are the references, and this is work we did for the RP2 structures. Okay. Then this is Matsumoto and Montesinos and Mibilla. So they did some kind of uniformization. So you can see the proof of this in this paper, and also Ushika did similarly. But I guess these are not so they differ a little bit from me anyway. So not much, but then the Thurston had originated this in the lecture notes chapter on orbifold. So okay, so what is a hyperbolic structure on the two orbifolds? This is just a geometric structure modeled on H2 with this isometry group PSL2R. So considering H2 as the upper half space, okay, so using the upper space model. So tabular space is just the deformation space of hyperbolic structures on two orbifolds. Okay, so it's the same. So more likely we should say it's a freecast space, but because tabular means more like a conformal structure. So by the uniformization theorem, it is actually the same, but we don't really want. So it's by the Kobe uniformization theorem. So as before, we can reinterpret the spaces as a set of diffeomorphism from M is a fixed orbifold and M prime is a hyperbolic two orbifold. And so any equivalence relation between these two is that there is isometry, so that H circle F is isotopic to G. So when the Riemann was just looking at these spaces, he didn't have this kind of external F here. So this F is more like a marking. So you can think of this as a marking, and so it makes a space bigger. Okay, so if you just look at the Riemann moduli space, it's just a set of space of conformal structure, but they don't really. You can modify all the diffeomorphism, not just the isotopies. Okay, so that's the difference. So the Teichmüller did this by doing this marking. So it's sort of covers the Riemann modular space, but it has a torus. It will have a fixed point. So the Riemann modular space is really a more orbifold actually. Um, uh, the quotient space is the same as above. So okay, so you want to define the Teichmüller space like this also, or you can just think of it as deformation space of a hyperbolic structure. Okay. The, necessary condition for an orbifold to have a hyperbolic structure is that the orbifold Euler character is negative. So that follows from the Gauss-Bonnet. So if you have a empty or geodesic boundary, then if you integrate the curvature is -1. So if you integrate the curvature, then it should be negative. So by the Gauss-Bonnet theorem, Euler character must be negative. So the negative of the hyperbolic area is the Euler characteristic times 2 pi. Okay, so that's the standard Gauss-Bonnet theorem for surfaces and orbifolds as well, because of the if you think about it, it's just because it's always covered, finally covered by the smooth surface, and then you have a you have this equation, like so the negative hyperbolic area is 2 pi times Euler characteristics times 2 pi. So I mean the minus 2 pi, sorry, it should be minus, and then the sorry, negative, sorry. So that holds for surface. So if you take the finite quotient, the Euler characteristic and the hyperbolic area divide by the same number, right? So number of covering. Okay. So therefore it holds for the orbifold, two orbifolds as well, right? So that's just the covering space theory using, you can prove that using that. Or you can directly prove that also, right? But I'm not doing that. So if you have a closed orbifold with a complex structure, then it has a unique hyperbolic structure, provided it's compact and has negative Euler characteristic. Okay, so of course the proof is again the Kobe uniformization theorem. So we're not, of course, proving that here. Uh, so the so the deformation space of complex structure on a closed orbifold is again identical with the Teichmuller space as defined here by the uniformization theorem. So you have a complex structure, then you can also define the deformation space of complex structure by same argument. So the atlas of charts so the complex structure is defined by atlas of charts with the transition functions being complex analytic functions, right? So you can define the same thing. So that gives you the Teichmuller space original definition. But here you can think of it as a space of geometric structure, because you can always unify as a portion of a hyperbolic plane. Okay, as long as the Euler characteristic is negative here, right? I'm saying Euler characteristic is negative. So then all the complex analytic map. So the deck transformation group is going to be isometry here, right? Because only complex isometry, complex analytic maps sending the upper half space to upper half space is the isometry. So there are only those, right? Okay, so that's the reason. So I'm not proving that so much. And so now we can do the geometric cutting and pasting and the deformation spaces. So you have some compact geodesic 1/4 with boundary points in the interior of 2/4 is either geodesic in the interior or is entirely in the boundary of the underlying space. Okay, so such things will be in the interior, because so if the boundary of the underlying space is silver case, that's the only case it can happen, then it will be actually in the interior of the orbifold, right? As an orbifold, it will be interior, right? So without any boundary points is just that case, or segment with the two silver points, which are either at silver edges or cone points over the two. Okay, so you can think of segment with two silver points. So it ends at either a cone point of order two, or it could end at the silver edge. Okay, so then these are entirely inside the interior of the orbifold, because these points are all the interior points, right? Not the boundary points. Okay. Of course, they are in the boundary in the underlying space, right? So boundary of the underlying space and the topological space and the orbifold interior are different, right? His orbifold interior can be bigger, right? Um, so I mean, of course, only in two dimension you have some notion of boundary, but not in higher dimensions. It's difficult to tell what's the boundary, right? So the topological interior is either in the interior or interior in the boundary of sigma. So in this case, also If it's entirely in the boundary, then it's silver boundary, right? So it'll be a silver edge, a silver arc. Okay, so those are the only thing that can happen here. Okay, uh, so I mean the one over without the boundary in the interior, right? So this is one notion, and then saying that so you shouldn't break the sentence here. It's just this one, and then you should break the sentence here. Okay, it's a bit ambiguous, but so then so in that case, the geometric type is classified by the length and the topological type. So what's the isotopy class of that segment or cross curve is in the underlying space, and what's the length? Okay, so such a geodesic so I'm so the one orbifold is classified by the length or whether it is a closed geodesic or segment with two several points. Okay, so that's so any such a one orbifold is actually covered by cross geodesic in some cover of a two orbifold, which is a surface. Okay, because a segment with two separate edge is covered by a closed curve by 2-to-1 map, right? So that's the covering in the orbifold sense, and of course, so if you lift this to so if there are some surface cover, then these will be the inverse image cannot have any silver points, so it should be compact one orbifold without any singularity. So that should be just one manifold, which is a circle. Okay, so that should be a circle. And of course, it cannot be a segment because it doesn't have any singular non-singular point in the upper space. So you can define the upper Teichmuller space of one orbifold as just the product of lengths for each component of L. Okay. So if I has a many component case, right? So I didn't. So you just have to classify by the length. Okay. So that's the and so we call the type of topological construction with one orbifold. So we talked about the cutting and pasting. So suppose there are boundary components of two orbifolds whose components have negative order characteristics. Then so now we're looking at things which may be have more than one components. Okay. So first construction was pasting or cross capping along simple cross curve. So pasting means you take two component curves and then glue them together. And cross capping is just gluing by order two self gluing the by the order two deck transformation. So you glue the points along the cross curve. And also silvering or folding along a simple cross curve. So silvering just means making it to mirror points, and folding means you use order two deck transformation, which fixes 2 points, and then you glue these together. So that was in another construction. And so B1 is you paste two full one orbifolds by just gluing them together. Okay, so that's so these should be in the boundary actually, right? And then the silvering or folding along one full orbifold. So silvering means we just make it into silvering. So in that case, the boundary full orbifold will become silver, but the endpoint will now lie in corner reflectors of order 2, right? And the folding just means that you glue the glue it by an involution fixing or fixing a point in the segment. So this will introduce cone point of order 2, and then the other one actually will just become a silvered edge, right? The silvered point ending at a boundary component of silvered edge, right? So those are the topological constructions, and now we can talk about the geometric version of this, right? So so suppose that involve one of there's a geodesic boundary components of hyperbolic two orbitals, so there should be no S here. And then if you paste two cross orbifold, so we can do it, but then there is R amount of different way to do it, but because you can always twist how much you go. Okay. So of course here you could think that if you go around the glue by like one half, just full circle, fully coming back, that will be the same. No. So as an isometry, if you can easily show that those are different in the Teichmüller space. Okay, so those are the same actually in the Riemann moduli space, quotient by the mapping class group. But if you are using this Teichmüller space with the definition using these augmented maps from with this working with that, then you can show that that's not the same. So actually, there's R. So you don't do R mod the length. Okay. So in the Riemann modular space, you have to do that, but in the Teichmüller space, you don't. And for cross capping the isometry of order two without any fixed point, that's unique. That's only unique isometry. So there's no real other condition. So this is there's nothing you can. So this is actually just rigid. There's no construction here. Okay, so that there's no parameters of things you can do. Just one construction. So, but here there are lots of different parameters of construction. Okay, and then for folding, we again have R amount of isometry because so if you have a cross curve, then the involution fixing 2 points, there actually are of them. Okay, so that's just not one. Okay, so there's many isometries, and then you have to show that these are all equivalent in the Teichmüller space. So I mean, for just S1, of course, there's just S1 of amount of thing you can do, but again, using the homotopy class, you see that these so if you keep twisting the angles, I mean these two fixed points, they're all different. Okay, so you have to see that. Okay, so those are so there's actually R amount of things you can do. And for silvering, there's this unique way to silver. Okay, so there's nothing you can do further. Okay, so those are the geometric construction for, and then P1. So again, the pasting along two geodesic full orbifolds. So there's this unique way to do it, and there's nothing more you can do. And then for silvering and folding, silvering again, there's only one way, and then folding. So the isometry fixing a point in the geodesic segment, there's only one way to do it. Okay, so there's nothing more you can do. Okay, so using these theorems, you can do these things. So take two orbifold sigma double prime obtained from pasting two cross curve boundary curve B prime on sigma prime. Okay, so it may have two or more components, and then if you glue these together, then the Teichmüller space from the glued this space, if you split along these what's glued together, then you get some subset where delta is a subset where these have equal lengths because you have to have equal lengths to glue it. And then this is a principal R fibration because because there's a R way to glue it. So there was I mean so for the same result there was actually a R way to get the sigma double prime. Okay, so that's why it's a vibration. And then the sigma double prime is obtained from sigma prime by cross capping. Then so result is a steepomorphism because there's just a unique way to do it. And then there's no more construction. And then also for every point here, you can always construct the sigma double prime. Cross capping always exists, right? Okay, so that's why it's on two actually, right? Right, and of course, here is so this is the image because whenever the lengths are the same, you can always construct back the diagonal space, sigma double prime. And then from silvering again, this is unique construction. So this is again diffeomorphism, and then folding along some boundary cross curve. So you have fixed points. Then this is of course with principal R vibration because there's a R amount of choices involved here, right? And then so for B1, if you paste 2 for 1 over for B in B prime in sigma prime, then it goes to delta, where delta is the length of B and B prime are the equal. Okay, so then it will always you can always construct a sigma double prime, but there's only unique way to glue by isometry. So this is just the diffeomorphism to delta. So it becomes even smaller. And then the sigma double prime obtained by silvering or folding. Then again, this is just the diffeomorphism, right? So SP is what you call the splitting map here. Okay, so it can split. Right. Okay, so I will take a 5 minutes break and then continue.